This video focuses on linear and nonlinear functions. Specifically, we're going to work on determining if graphs and equations are linear or nonlinear functions. First, we need to know the definition of a linear function. A linear function is any function that graphs to a straight line. That's where they came up with the word linear. We see the first four letters are the word line. It's because all their graphs look like a straight line. So, if they are kind enough to ask us which graphs are linear relationships, if all the functions are shown as graphs, we simply need to test which ones are straight lines or not. We see A, C, E, and F are straight lines, every one of them, so I could say each one of those is a linear function. We see that B is a curvy line from the equation y equals x squared minus 5, and we see that D is also a curvy line from the equation y equals 1/10 times x cubed. Both of those, B and D, as some of you saw yesterday, need to be placed as nonlinear functions. We also see function G where the two lines or the graph is broken in half and both halves are curving. That's nonlinear. That came from the graph or the equation y equals 6 divided by x, which we could write in a different way. We could also just say x times y equals 6, two ways to say the same equation. The last one, a little tricky, function h. It looks like it's comprised of two rays, 2 points that start here and go off in one direction. But because those two rays are changing direction, a negative slope into a positive slope, function h would also be nonlinear. The trickier question is if they ask us to determine which functions are linear or nonlinear and they provide equations without the graphs. We have to understand what's going on in these equations to be able to determine if they would make linear graphs like A and C and E, or if they'd make nonlinear graphs like we saw with B and D and G as examples. One of the best ways, if you don't start to recognize already the rules that turn these linear equations into nonlinear equations, is to use the graphing calculator Desmos. It's a tool that's on your Clever backpack, so if you go there, right near 10 marks, we see Desmos graphing calculator. If I open that up, Desmos is a computer program that will find solutions to any equation you put in as quickly as you could imagine and then put a graph. So if I look at this first equation, y equals 15, if I started to type that equation into Desmos, and if I zoom out properly, Desmos will show me the graph y equals 15. That's this red line right here. I can go ahead, hit enter, and Desmos will let me graph another line. This time I'm going to go ahead and graph y equals 2 divided by x, that function. 2, hit the slash button, divided by x, and I see in blue here, we could zoom in a little more, in blue here we see a nonlinear graph, so that would tell me that 2 divided by x is nonlinear. I want to show a couple common examples of nonlinear graphs. Whenever we see x squared or x cubed, for example, this is y equals x cubed minus 5. If I go ahead and enter that equation, y equals x raised to the power of 3, I use the button shift 6. If you hold the shift key and hit the key for 6, that little arrow means you want to write an exponent, and I see right away the graph is now starting to curve. So as I enter the equation y equals x cubed minus 5, I see already once the x cubed is in there, the graph is curving, and minus 5 just kind of brings that graph 5 units lower. Another example to point out, something that always would make a nonlinear relationship, is anytime the exponent is raised to the power of x. If we keep changing what our exponent is, similarly to if we take x and raise it to a different power than 1, we're going to see some nonlinear graph. So if I put in the equation y equals 1/2 all raised to the power of x, we see this purple graph here, 1/2 raised to the power of x. Anytime we put a variable in the exponent, we also get a nonlinear graph. Desmos is a great tool if you're trying to start exploring these new equations and start seeing what their graphs might look like.